the first to apply game theoretic analysis, industrial organization, bargaining theory, and contract theory. Has also co-authored papers on repeated games, reputation effects, and behavioral economics. Has received many prestigious awards and fellowships, and also co-authored many books, including Game Theory, which is a textbook used in many economic graduate studies, and also co-authored the book Theory of Learning Games, from which I've personally learned a lot. So before getting started, let me remind everyone the format of the seminar. So please remain muted during the talk and type down any questions you might have in the chat. And I will probably relay them to Professor Fudenberg when appropriate. And also at the end of the talk, we will have a Q&A session, and feel free to unmute yourself and ask questions. The talk will also be streamed on YouTube and recorded. So if you would not like to appear in the stream, feel free to join us from the YouTube channel. So without further ado, please join me in welcoming Professor Fudenberg. Thank you very much for joining us today. The floor is yours.
Yes, thank you for the introduction, and thanks everyone for coming. So this paper, Which Misperceptions Persist, is a joint work with Giacomo Lanzani, who's a phenomenal graduate student, and he's here and can help answer questions in the chat or afterwards. So our starting point is that economic agents are often misspecified in the sense that their prior beliefs can rule out the true data generating process. And the literature has pointed to various reasons different forms this misspecification might take. People might be overconfident. They mistakenly believe that their own ability is much higher than it really is, and leads them to draw wrong inferences. They might believe that some correlated variables are actually independent. That's a phenomenon called correlation neglect that's been documented in a number of lab experiments. Or they might have a model of the world that oversimplifies. They might think that GDP depends on 4 covariates. It really depends on 7. So if they're missing 3 of them, they're misspecified. Now, these incorrect views, at least sometimes, seem to persist even when people have a lot of data. A Bayesian who's correctly specified, whose prior gives positive probability to a true data generating process, will eventually learn the truth. So if you're consistently wrong with lots of data, you're not a correctly specified Bayesian. But it is consistent with Bayesian learning with the misspecified prior. If your prior rules out the truth, you're never going to be able to learn it. But that raises this question: we have these people who are misspecified. They're getting lots of data, and they're never learning, but they're wrong. So what's going on with that? When is that a good prediction? Well, just mechanically, Bayesian updating can never fix this problem. Bayesian updating cannot lead you to put positive probability on a data generating process that lies outside the support of the prior. There's no Bayesian way for people to say, oh, my support of my prior was too small, I should add more things in. So we need a non-Bayesian way, and we're going to use an evolutionary criterion to evaluate the stability of misspecified Bayesian models. So these misperceptions of a title is a misspecified Bayesian model, and we're going to try and see which sort of misperceptions are more likely to persist. To summarize the model loosely, I'll be more formal in a bit. We're going to have successive generations of agents, and we'll let the agents become more open-minded than their parents. They may enlarge the support of their priors and consider things their parents didn't think were possible. So our agents have beliefs over parameters, where the parameters are associated with action contingent outcome distributions, one distribution per action. We call these the support of the prior their subjective model. The agents observe the actions and outcomes of the previous generation and update their beliefs and play a best response. Different agents may employ different subjective models. The evolutionary part of our model, of our own model, our paper, is that the relative frequency of models that induce better actions, that give higher payoffs, increases over time. So to write down a dynamic process and show that the steady states of the process coincide with the Burke-Nash equilibria. It's the term due to Spondo and Puzo, and if you're not familiar with it, I'll be defining it in a bit. So all these Burke-Nash equilibria are steady states, and in them they just might be misspecified. So that's just our starting point. What we do then is bring in mutations that have agents have a larger model. They use the expanded model to make inferences, and we ask whether the use of the expanded model will spread or whether the existing model resists mutations. And we'll see that not all the equilibria are unstable, because the share of mutants only increases if the mutants do better than the agents who are using the old model. We're going to consider two particular ways that subjective models can be expanded: local expansions to nearby subjective models, and what we call one hypothesis relaxations, where the agents drop a hypothesis that characterizes the model. Like they might have originally been sure that X1 and X2 were independent. They could drop that hypothesis and allow for the possibility that they're, say, positively correlated. We characterize stability in both cases, and we apply the results to several common misspecifications. I'll do a couple examples in the talk. Of course, the paper has more. So this very briefly, so the closest related work was a classic paper by Burke in statistics on Bayesian updating with fixed IID data when the agent is possibly misspecified. And he shows that beliefs concentrate on the elements of the support of the prior that minimize the KL divergence from the truth. Espandopouzo defined Burke-Nash equilibrium that combines this Burke result about minimizing divergence with the idea of Nash equilibrium, and they relate it to the long-run outcome of learning from misspecified data. After Espandopouzo, there's been quite a flurry of work on misspecified Bayesian learning. Some by me, Philip Strack, Kevin He, Espandopouzo, have another paper with Yamamoto, and also Frikajima and Ishii have papers that look at convergence of actions and beliefs in more general settings than these papers on the previous bullet. And lastly, Giacomo and Philip Strack and I have a related paper. And there's lots more. I could take half an hour to review the work of the last 5 years. I'm not going to do that. Okay, here's yet some more. Espanda Vespa Yüksel is an experiment that finds misspecified agents make small partial adjustments in the face of unexplained evidence, as in our analysis of local mutations. He and Libgober and Maruka and Yamamoto look at misspecified learning in a game. Schwartzstein and Sundaram suppose that alternate models spread on a social network. And if you're exposed to more models, it hardens the reaction to data. And Gagnon, Barsh, Rabin, and Schwartzstein introduced the idea of attention partitions, the things people pay attention to, and agents can become correctly specified depending on how they allocate their attention. So that's just a nod of the related work. And if you haven't seen it, it's probably not so comprehensible. At least it's a pointer to things you might want to read. So now let me get a bit more precise. So we look at a single agent decision problem. Agent chooses an action A after observing a signal S, and both the action space and the signal space are finite. So the agent's strategy each period is to pick an action for each signal. So it's A to the S. With outcomes are generated after the action is taken, outcomes Y. The utility depends on the signal, the action, and the outcome. There's an objective data generating process that has two parts. There's a distribution over signals, sigma, and there's the distributions over outcomes. Of course, the distribution over outcomes depends on what action you take. So there's a different distribution Q star over Y for each different A you might take. And then I'm going to denote the expected utility of the agent to a strategy pi by capital U star. There's nothing original or surprising there. It's just this kind of utility. Okay. The agent uses parametric models to describe their environment. A subjective model is a set of parameters, capital theta, that they assign positive probability. And each little theta is associated, again, with a family of these probability distributions. The agent's uncertainty about the value of the parameter described by belief mu, the subjective expected utility of pi is capital U sub mu. Let BR of mu be the set of best replies to mu. Okay. Given two distributions on outcomes alone, on delta of y, define h of q and q prime to be minus so the integral of log q prime of y dq of y. Q prime with smaller values of h better explain the true distribution q. Given a distribution of strategies in the population, we let h sub psi be the average value of h. Okay, so we have to say for each strategy, different people are playing different shares of the population are playing different strategies. Pi, we add those up. There's different possible signal realizations. We get a weighted version of h. And capital theta sub psi is the set of little theta and capital theta that minimizes this function over capital theta. Okay, minimizes h psi. We call this the KL minimizers for reasons that you may or may not recognize this. This is really a version of the Kullback-Leibler divergence here. The Kullback-Leibler divergence would traditionally have an extra constant taken off the end, but minimizing, for the minimization, the constant term doesn't matter, so we've dropped it. When an agent with subjective model theta observes data from a large population whose strategies are distributed according to psi, their beliefs concentrate on the set capital theta of psi. That's the result. Oof, okay. Now let's talk about the whole overall system. There's a continuum of agents. Each agent observes a distribution over outcomes in the previous period, which matches its theoretical distribution. The state of a system at period t is a finite support joint distribution over models and strategies. And I'm going to want to have notation for the marginals, p sub capital K and p sub pi. Agents' beliefs are supported on the minimizing parameters with respect to their theta, and given the data they saw, they play a best response to their beliefs, and let p super t plus 1 be a distribution of actions played at t plus 1 by agents with subjective model theta when the previous state is pt. I promised a definition of Burke-Nash equilibrium. A Burke-Nash equilibrium is a pair, a support capital theta and a distribution of strategies psi, such that for every individual strategy pi that has positive probability according to psi, there is some belief you could have with support on the Kullback-Leibler minimizers, capital theta of psi, that makes pi a best response. Okay, this importantly, the set capital theta of psi needn't be a singleton. There might be multiple things that achieve the same Kullback-Leibler divergence. Okay. If you're correctly specified, then the Kullback-Leibler minimizing thing has zero divergence with what's going on, and there's only one way. There's only one way to be correct, right? It's the truth. But in general, there can be multiple beliefs you could have that match the data equally well, but not perfectly. And then you play best response to either this belief or that belief, or even some convex combination of the beliefs. The equilibrium is uniformly strict if for any mu in delta of theta of psi, for any belief you could have, you have a singleton best response, and it's the same singleton. Okay, BR of mu is a singleton point, and everyone plays that. So in principle, there might be two different KL minimizers, but you might have the exact same best response to both. So this would also be uniformly strict. We aren't saying that capital theta of psi is a singleton. We're saying there's a unique best response to beliefs that are concentrated on capital theta of psi. Okay, evolutionary dynamics. The share of agents with a particular model evolves according to a payoff monotone dynamic. What that means is basically this strategies that do better, their relative share increases. So any strategy whose payoff is better than the population average, its share of the population increases. Strategies whose shares are less decrease. So a standard example of a monotone dynamic is the replicator dynamic, which you may be familiar with, but there's lots of others. In our evolutionary model, the next generation does not inherit the beliefs of their parents. What they inherit is this set capital theta, the set of possible things, and they then look for the best fit in the set capital theta given the data. So they do Bayesian updating to get the best fit given their model. A solution to this system is just a sequence of states where the shares evolve according to this payoff monotone dynamic, and each agent plays the best reply to their KL minimizing beliefs. And a steady state is just a constant solution of a system, or it's a fixed point of this map. So we still haven't really done anything. This is just setting the stage for where we want to go. To show we set the stage correctly, we'll point out steady states are isomorphic to these Burke-Nash equilibria. So this is really our starting point of the paper. There's all these recent papers analyzing Burke-Nash equilibria where people are consistently misspecified. We wanted to know, are all the different misspecifications equally likely to endure? So right now, we haven't yet brought in mutations. So steady states are the same as Burke-Nash. What we want to do is use mutations to see if we can eliminate some of the steady states. So we'll say that P bar is an epsilon mutation of a steady state to a larger subjective model. So it's a mutation from capital theta to a larger capital theta prime if a fraction 1 minus epsilon of agent sticks with the old model capital theta, and a fraction epsilon uses the new richer model capital theta prime. And once again, all the agents play best responses to beliefs, and their beliefs are concentrated on the KL minimizers given their subjective model and the data. The people with different subjective models could have different KL minimizers. So let me pause here, make sure there's no questions just on the setup. Anyone have any questions? Is it clear, at least conceptually, what's going on, if not all the notation?
Okay. There are no questions in the chat.
Good, okay. So now, a Burke-Nash equilibrium, which is this model capital theta and a distribution of strategy psi, resists invasion by this larger theta prime if after the sufficiently small mutation, the aggregate behavior converges back to where it was. So mutants come in and they die out. Fine. An epsilon mutation to a larger model, it says improving, but this is a typo or an editing error on our part. This should actually be explanation improving. It's explanation improving if the new richer model allows a better fit to the data. If it allows a lower KL divergence than the old model did. And it's pretty immediate, given the way we set things up, that a Burke-Nash equilibrium resists every mutation that is not explanation improving. Because if it doesn't fit better, when you go and estimate the KL divergence, you have the same minimizers you used to have, you do exactly the same thing. So the only kind of model that could possibly invade is one that provides a better fit, that gives a better explanation. That's a necessary condition. It's not a sufficient condition, but it's necessary. So let's dig in some more and see what more can we say. And to do that, we have to be a little less abstract about what kind of mutations we consider. So the first kind we consider, we call local mutations. So we just take the all set capital theta and add in every point that's within epsilon the point of theta. So we've grown the theta out by epsilon. And we'll say that the Burke-Nash equilibrium resists local mutations if it resists invasion for every sufficiently small epsilon expansion. So resist small local mutations. Well, one reason an equilibrium can resist local mutations is that all mutations lead the agents to stick with the best responses they used to have. Okay? So that was the case if the mutation is not exponentially improving, but even if it is, every uniformly strict Burke-Nash equilibrium resists local mutations. Why? In a uniformly strict equilibrium, action A is a strict best response to every KL minimizing parameter. So if we bring in a small mutation, you might get a slightly better fit to the data, but your best action is still going to be A because utility function is continuous, right? So that's not the end of a story because uniform strictness is a very strong condition, and uniformly strict Burke-Nash equilibria need not exist. At other Burke-Nash equilibria, multiple strategies are a best response to some belief over the KL minimizers, and only some of these are best replies to the minimizers of the expanded model. The relative performance of these new best replies, the ones that an expanded model, and the old ones is what determines resistance to local mutations. So after an expansion, the mutant's beliefs are concentrated on the parameters that help explain that make the greatest improvement in explaining the data. So what will they play? Well, they'll play a best response to the best fit. Okay. Exactly what the best response is depends on how big epsilon is. It depends. So the local responses, we see for every epsilon, let's look at the minimizers on capital theta sub epsilon, play best responses to that, and we take the limit for really small epsilon. That's the local responses. If all the local responses at an equilibrium give people a higher payoff, the equilibrium does not resist local mutations. You guys can come in. If the equilibrium is quasi-strict and some local response gives a lower payoff, then the equilibrium resists local mutations, even though the expansion can allow a better fit. So what does quasi-strict mean? Equilibrium is quasi-strict if all the best replies are played with positive probability. How is that used in the proposition? Well, if the response had worse payoffs, but the equilibrium is not quasi-strict, that means there's a new response that wasn't being played before, then the feedback from the mutated agents can reveal information that can change the behavior of the old population. So the system isn't going to work. So this is how quasi-strict is used in the proposition. So that's super abstract. Let's illustrate this with an example. This is may seem that the priors here are kind of weird and silly. It's a toy example, but it's an example that has a distinguished history in this literature. So this is a monopolist faces a linear demand function, takes action A, gets payoff AY. Monopolist does not know the intercept I and the slope L of the demand function. They have two actions, 2 and 10, and it's objectively optimal to use action 2. Now, the reason this example is interesting to us and maybe on the insiders of the literature is one of the early papers on misspecified learning with endogenous data, where the data depends on the action, is Nyarko 94. And he considered this example, it's this leading example in his paper. And then the very influential Esponda-Puzo paper looks at a related version of the same example. It's the exact same setup, but slightly different in the way I'll show you. Okay, so the difference is in Nyarko's version, there's a unique Burke-Nash equilibrium. It's in mixed actions. and it does not resist local mutations. In Esponda-Puzo's version of this monopoly example, there's a continuum of Burke-Nash equilibrium indexed by the share of agents using each of the two actions. And it turns out that local mutations can invade if and only if the suboptimal action is being chosen by enough agents. So that's a high-level summary. These pictures may help a little bit. So here's the Nyarko case. So the gray rectangle is the support of the agents prior. Okay. The blue ellipses are points of a constant KL divergence. Remember, the estimation, maximizing likelihood, leads you to pick the parameters that minimize the divergence over the parameters you think are possible. So in this picture, the KL minimizing parameter is there on at the point theta alpha on the right-hand face of the rectangle. And here, if you enlarge the subjective model a bit, the direction of improvement is to think that L is greater, the intercept. And if you think L is greater, you're going to pick the low price, which is the optimal decision. So a small mutation here will lead the mutants to, instead of mixing, to charge the low price at probability 1. They'll do better, they'll invade. In the Esponda-Puzo example, the KL minimizing point was up on the right-hand vertex of the rectangle at a corner. There's a continuum of equilibria here. The equilibrium where most people play action 2, but not all. So share of people playing action 2 is 35-36. That resists local mutations, because if we compute the KL divergence, given the data, remember the data, these blue ellipses depend on the data, depends on the actions being played. So given the equilibrium action, we compute these ellipses and we say, okay, what's going to happen if we enlarge the model a bit, you're going to think that the intercept is higher than it is. That's going to give you a better fit to the data. It gives you a better fit to the data, but it leads you to make the wrong counterfactual prediction. Once you think the intercept is bigger, you decide, oh, it's good to charge a high price, right? This makes sense with demand curves. Intercept goes up, you more to gain with the high price. So then the mutants don't survive because they're being induced to play the wrong action. If instead we looked at a mixed equilibrium where only a small fraction of agents are playing the wrong action, very small, then the mutation makes oops. So I seem to have the same point being made on both bullets. And the point was really to switch from the one case to the other. So I apologize on that. So that's an example of what happens with local mutations. We also consider agents whose subjective model is described by a finite collection of hypotheses about an underlying parameter. What's an example? Well, maybe you're sure that your skill is at least 10 on some numerical scale. There's a few papers on overconfidence lately, people who have this form of overconfidence. They're too sure in their own ability, so every time things go wrong, they decide it's their coworker's fault. Or it could be a joint restriction on parameters, like independence between two variables. And these different hypotheses describe parts of the model that can be relaxed by mutation. So formally, we say there's a collection of continuous functions, and F, where theta is just the intersection of these inequalities, Fi of theta is greater than 0. And a subjective model is a one hypothesis relaxation if you just drop one of these inequalities. That's what it sounds like. And a Burke-Nash equilibrium resists one hypothesis mutations, if it resists invasion from every one hypothesis relaxation. Now, you may be thinking, if I hand you a theta, is there a unique way of describing it with a finite collection of linear inequalities? Well, no, not in general. There can be multiple collections of hypotheses that can describe exactly the same set, capital theta. And then, if we have different collections of hypotheses, it'd be different sets of one hypothesis relaxations, and there'll be different implications for resistance to one hypothesis mutations. So we view this as natural because we want you to think of the agent's thought process is really not about theta. The agent's thinking about these hypotheses F. So the F is the way the agent thinks of the world. And so these Fs are the things that the agents can decide to relax. They don't have a parametric set, capital theta, in mind. Given a steady state P, the L-agnostic minimizers are the minimizers we get when we drop hypothesis L. So let theta psi be a uniformly strict Burke-Nash equilibrium. And remember that uniformly strict equilibria resist all local mutations. So if for some L, all best replies to PL of P induce a larger payoff than the steady state, then the steady state does not resist one hypothesis mutations. We're doing this particular mutation L, and it invades. But if for every L, there's some best reply to PL of P that does worse, then the steady state resists one hypothesis mutations. So those are two easy state cases. They're not exhaustive. So on this more general result, it's a hyperlink with a heavier statement of a more comprehensive result that we can come back to if we want to later. So how about an example? So taxation and overshooting. Our agent chooses an effort A, either 3, 4, or 5, at cost 2A over 3, and gets income A plus omega, or omega is just a normal shock. They pay taxes X, which depend on a tax schedule tau star. And the truth is that tau star is a kind of funky piecewise linear function with a sharp kink at 16/3. Okay. The agent's payoff is their income minus their tax minus cost of effort. And if you do the calculation, the optimal effort level is intermediate, it's 4. The agent observes Z and X in each period. Suppose the original paradigm, the original set capital theta, is the agent thinks the tax schedule is linear. They don't know the coefficient, but they think taxes are just linear, so constant average tax rate. Well, then the KL minimizing parameter treats the expected marginal rate as the actual average rate. And if you do the calculation, the unique pure Burke-Nash equilibrium is uniformly strict, and the agent works too hard because they are underestimating the progressivity of a tax schedule. Now suppose the agent relaxes a hypothesis. They drop the restriction that the quadratic term is 0 and say, well, let's be more general. Let's estimate a quadratic function. Give that that's linear, so it can't fit worse. In fact, it fits better. If you estimate a quadratic function, it will fit better, but it will end up having a very high quadratic term because given that people are taking effort 4 and given where the tax schedule was, most of the realized income levels will be near that kink. So when you fit the quadratic function to that data, you're going to overfit the progressivity. You're going to think taxes are more progressive than they are, and then work too little. So, and it turns out, so before with linear, people worked too hard. With quadratic, they didn't work hard enough. It turns out that working hard enough is even, working too little is even worse than working too hard. So the quadratic model, the better fit, leads to a lower payoff. So the equilibrium resists one hypothesis mutations, even though it's a strict equilibrium. Here's a picture. Okay, the tau star is the actual tax schedule. So it's not for realistic thing, having this sharp, it's one sharp kink. The dark blue line is the best linear estimate. And the light blue line is the best quadratic fit. Okay, again, the quadratic fits the data, observed data better, but it leads to a worse decision. One last example. Additive lemons and cursed equilibrium. This is from an earlier paper of Esponda, before Esponda and Pruso. So the agent is a buyer with valuation omega plus 5. The seller owns the object and values it at omega. And this will be a double auction with price at the buyer's bid. So the seller sets their bid equal to their value. The distribution of omega is probably half it's 3, probably a quarter it's 2, or probably a quarter it's 1. Importantly, the value of the good is only observed when a sale occurs. If you buy the good, you see what it's like. If you don't buy the good, you don't see how good it was. Okay, so here a parameter is a probability distribution over prices and a conditional distribution over values given price. The true distribution of values depends on price, right? Because the high value sellers aren't going to be accepting low bids. The agent believes that price and value are independent. That's an example of correlation neglect or cursed equilibrium. The objectively optimal strategy is to bid 3. But for our agent with the wrong beliefs, bidding 2 is a Burke-Nash equilibrium. When the agent does this, they're going to correctly estimate the distribution of seller bids. They see the distribution of seller bids each day. They see the fraction of time that the sellers bid 1, 2, and 3. But they miss the correlation between seller bid and seller value because their prior said there is no correlation. And so if you are sure there's no correlation, you can't learn what the correlation is. Now consider a mutation that drops the assumption that the seller play is independent of their value. Well, it doesn't really do anything because the buyers weren't bidding 3 before. So there's no data on what happens when someone bids 3. So the mutated agents have this more general model. If they had data on sales at price 3, they would learn that value is higher there. They have no data there. So they have no reason to change their minimizing parameter and no reason to change their bid. Now, of course, if we added a point mutation that includes a true data generating process, then the only way the agent is going to see a correlation between bid and value at low and medium prices, and this will lead them to correctly infer there's a correlation between bid and value at high prices. Okay. One more application. Please, yes.
I think that this is a good moment to try to answer a good question by John in the chat.
Good.
So, do you want to open it or do you want me to rephrase it?
Yeah, so maybe I can repeat the question so that all the audience can hear it.
Yeah.
So actually, John asked a question: when you start a round prior with mutations, you have 2 outcomes: misperceptions persist or corrected. It seems to me that for many economic activities, misperceptions can lead to different beliefs and actions, which in turn confirm the misperception. Hence, a self-fulfilling prophecy. Could this possibility be worked into the model? Or John, you can unmute yourself to ask a question if you have more details.
Okay, so actually what I was thinking was that I'm looking for a model that will help me and to describe the following situation. And you started with some misperception of the reality, okay? So through the advertisement, propaganda, whatever. And then because of that misperception, of course, that you're going to form the new belief, you update your belief, and then you're going to have a different actions. And all those beliefs and actions in the end actually confirm the misperception. So which means you start with something wrong, but that something wrong needs you to take actions in a way that ultimately confirms the wrong perceptions. So that's the possibility that I think in this particular model, I don't see it. I just wonder if it's possible to work at this kind of thing.
I'm not entirely sure I understand the question. There's a few different parts there. So one thing is, you say, could the actions confirm the misperception? Well, yes. That's before there's the mutations in these Burke-Nash equilibrium. People have misperceptions. They're behaving optimally given the misperceptions, and they have no reason to change their beliefs. So in terms of the last sentence or two of your question, I think our baseline model already does that. Now, you had some other ideas too, and I confess I didn't track all of them. Would you like to try again?
The concrete example I have in mind is that, for instance, let's suppose the economy is really terrible today, and based on all the data that we have, and it's actually pretty terrible. But let's suppose that those data is confidential to me. Let's suppose I'm the government. I know all the data. I'm not going to disclose the data, but I'm going to tell everybody, in fact, the economy is doing great. Okay, so which basically everybody is going to start with a misconception, and from that point. Okay, but because of the fact that everybody thinks the economy is doing great, of course, that I'm going to make an investment, I'm going to do a lot of different things, and then that ultimately the economy turn out to be good. That may actually turn the sort of misconception into the right conception. I'm just wondering that kind of a process, because
that's an interesting process. That's definitely not covered by our model. So we don't have this. I mean, we don't have this one distinguished actor like the government. We don't have any private information. The agents a simplifying aspect of our model, the agents don't get any, the agents base their decision on data from the past generation. So they have to decide whether to go be lawyers or doctors, and they look at what happened last generation. They don't have a sequential decision process of their own. Each agent makes a single one-time decision. And so they have no incentive to experiment and get new data because they're only deciding once. They base all their decisions on the old data. So there's lots of richer models that one could look at. And your idea of the government misleading people and trying to get them and manipulating beliefs is very interesting, but it's pretty far from what we're trying to do.
Absolutely, yeah. So is there any model like that out there?
I don't happen to know of one. Giacomo, do you?
Not really, no, not really. So in our model, there is a force of self-fulfilling prophecy, but it's different from external manipulation. So our misperceptions are generating equilibrium data. And by generating equilibrium data, they can generate data that even in an expanded model induce worse action. And by inducing worse action for the expanded model, they make the misperception resistant. So there is a self-fulfilling element in our model. It's just not driven by an outside agent that is enforcing it. So it speaks to self-fulfilling property with misperception, but in a very reduced form compared to a situation in which you have someone external.
Great, it's good to know. Yeah, thanks.
So just a few extensions, other things to talk about. So this Gagnon, Barsh, Rabin, and Schwartzstein introduced the idea of attention partitions, the idea that agents don't pay attention to the actual outcome. That's too costly. Instead, they partition the data with the attention partition calligraphic A, and they only distinguish between parameters that yield different best replies. So then instead of looking for parameters that best fit the data given capital theta, you look for parameters that minimize the divergence between your model and the distribution on this coarser partition. In the tension improving mutation, the subjective model allows for lower divergence along the attention partition. It turns out that local responses on these attention partitions and the local responses on the full set of observables can differ. So these two kinds of mutations have different implications. So this is probably really only mostly mentioned to people who know this paper by Gagnon, Barsh, Rabin, and Schwartzstein. In that paper in GRS, they assume that the actions people take has no effect on the distribution of outcomes. And in that world, a suboptimal equilibrium resists a mutation to the correctly specified model if and only if it has the right distribution on the attention partition. If a data generating process is endogenous instead, then this result gets modified. So it's not the correctly specified model that's all that survives, but only self-confirming equilibria survive. These are ones that allow a perfect match to the equilibrium outcome distribution, but could be wrong about what would happen with other actions. But in general, attention partitions have ambiguous implications. Some equilibria resist local mutations, but not expansions with attention partitions. And conversely, some resist local attention mutations, but not more general ones. Okay, a few technical points to close with. You know, I wrote down a continuum model and said everyone's people play best replies to the KL minimizer given the true distribution last period. So you might want to be reassured that there's some kind of finite sample limit process that yields the model. And so we can actually show that, at least in some cases. If the support of the prior capital theta is finite, or there's unique best reply to the minimizers, then we can take a model where instead of each agent seeing a continuum of observations, each agent gets n random draws. So different agents will have slightly different data and may behave differently, but we can still show a distribution converges to the distribution that we've been analyzing. And that we prove that using an argument similar to Burke's original argument about convergence of beliefs. And we also use the fact that the likelihood ratio between the KL minimizers is a random walk. Something behavioral economists care about, I think more than theorists we found, is that our baseline model has a finite number of actions, and in many applications, it's nice to write down a continuum of actions. Right, so the monopoly example I showed you is only 2 actions. That was from some theory papers, but in applied papers, the people use real numbers usually for actions. And it takes a little bit of care to extend our results to continuum of actions. With the one hypothesis mutations, it's no problem at all, if the cardinality of the action space doesn't matter. But with local mutations, it does. Because with a fixed set of actions, if we have a very, very small epsilon mutation, epsilon change in beliefs, it's going to be small compared to how far apart the actions are, which is why every uniformly strict equilibrium resists local mutations. But if the action space is connected, then in any uniformly strict equilibrium, there's a nearby action that does almost as well. And then even an arbitrarily small change in beliefs will make some change in best reply. So local mutations can invade some uniformly strict equilibria if we move to a continuum of action setting. But we're reassured that this is maybe a sensible conclusion because these unstable equilibria in the continuum limit correspond to a limit of unstable equilibria in the games with finite action grids. So I think it makes sense to exclude them. So just to wrap up, we have a model that combines learning and evolution. And we use mutations to help understand why some misspecifications may persist for a long time. These are the ones where even though they give a better fit to the data, they lead to worse payoffs, right? And we characterize stability with respect to two sorts of mutations, the local mutations and the one-hypothesis mutations. And we extend the analysis of attention-channeled mutations to allow actions to influence outcomes. And that's what I wanted to tell you. And I guess we still have some time for questions if there's any more questions.
Thank you very much. Let's see whether the audience has any questions. Please feel free to unmute yourself and ask. Saknaya, you can unmute yourself.
Good morning, Professor. Just to clarify on a single point, I remember seeing that you had used common priors for beliefs here. So is it like the common prior continuously gets updated with these mutations, and the mutated common prior is used for as a source of about the belief for the next generation, or is it like the original common prior is used here as a source of belief?
So it turns out, because our agents, each generation of agents gets an infinite amount of data. So the only aspect of the prior that matters is the support of the prior, because we know that with an infinite amount of data, their posterior will be concentrated on the set of KL minimizers. It doesn't matter, like if you thought the truth was supported on the interval 210 and the actual truth value is 11, it doesn't matter what distribution on the interval 210 you had. The KL minimizer will still be a point mass on 10. That's the closest point to what's really going on. There's more complicated examples, but say in general, this is the simplification that comes from assuming the agents observe an infinite amount of data that the prior no longer matters. That's why in our process we say the actions played have to be some best reply to some convex combination of beliefs, to beliefs that are supported on the KL minimizers. And we're not committing to, is it 2/3 this minimizer, 1/3 that, 1/3 this, 2/3 that. Of course, if the KL minimizer is unique, then there's no issue at all. But yeah, so the priors don't really matter.
Okay, thank you.
Any other questions from audience? Feel free to ask.
Hi there. Nice talk, Drew. I want to ask, underlying in the model is really a decision problem, right? My utility
Yes.
depends on my action in the state.
Exactly. It's not a game. It's correct.
You call it Burke-Nash equilibrium. So with equilibrium, of course, I wonder, can you extend this to games?
We called it Burke-Nash equilibrium, even though it's a one-player game. This is because the term was coined by Spandapuzzo. Their version works for more than one player, but in fact, most of their examples and most of this literature looks at only single agent decision problems. I mentioned a few papers there in my brief lit survey that looked at misspecified learning in games, but most of the ones I had up were on single agent problems. But every one of those papers since Spandapuzzo, and I'll make up the numbers, 10 or 15 papers on misspecified learning since Spandapuzzo, and they all use this language. Just because this even though it's not really a game, the Spandapuzzo insight of that has been sort of the unifying principle for the work. So we're just following the literature. So I'm saying, don't blame me, blame them.
No,
But,
no blame. No, I just thought it relates to the earlier question about the government trying to sort of because if it was a game and sort of the Nash equilibrium is inefficient, well then would that be a model where that question would have bite?
Definitely apply Burke-Nash equilibrium to games. And a few papers do, so we have not done. Now, I guess the idea of having a big government player and a bunch of small players and evolution and mutations, it seems complicated, it's not undoable. Yeah, so.
But I don't think you would need big player and the small player. I mean, you could just have a game, and if the base Nash equilibrium is inefficient, then the Burke Nash might be better, and
Sure.
you know, seeding misperceptions.
Well,
I mean, that seems to be a
Here's a
sandbox
simpler
to
point.
cook that up.
Here's a related point, sort of tangential observation that I find interesting. So let's not worry about efficiency and better. So we're privately optimal. So we know there can be an advantage to be committed to play in certain ways in some games. Some kinds of misspecification can lead you to play like a Stackelberg leader. And so it can be, if your opponent, you know, knows you're misspecified or learns you're misspecified, this is in your advantage. So yeah, all these things about commitment being good, or, you know, have echoes from misspecified learning. I could, you know, maybe in the actual equilibrium, when people don't like red cars, I should go out of business because I make red cars, and then you take over. But I'm misspecified and don't realize that, so I stay in it, and so you end up leaving the industry. I mean, there's all sorts. There's lots of examples where misspecification can be privately beneficial in a game. It's, you know, it's more in a decision problem. Of course, it can't help you. I mean, we've been talking about how some misspecifications survive. You'd be better off, or you're always weakly better off with the correct model in a decision problem. So to me, that makes this more interesting. I mean, the fact that you can be better, you know, misspecifications can survive in a game is maybe not so surprising, exactly because it's not necessarily in your best interest to play myopic best response to what other people are doing.
Any other questions from audience? I guess I have a quick question regarding it seems to me that overall the framework and the analysis based on the KR minimizer, KR divergence, right? Yeah. Is that possible, or could we extend to other distance metrics like Washington distance or other? Would that fundamentally change everything, or?
Where the KL comes from is Bayesian updating. So this isn't like an arbitrary choice of definition. Bayesian updating leads you to minimize KL divergence. If we had people not do Bayesian updating, if they use a different kind of updating rule, then you would have a different selection criterion. But this is just a basic fact. If you look at the way the maximum likelihood estimate of the parameter is the one that minimizes the KL divergence.
KL divergence. I see.
And Bayesian is going to concentrate their beliefs on the maximum likelihood estimators when they have lots of data. So, so this is, you know, now we took for granted people are Bayesian. That's the most common assumption, especially in economics. It makes life easy because Bayesians are dynamically consistent. If we drop Bayesianism, we lose dynamic consistency. So that's hard. But there's all sorts of, I mean, we know people don't really do Bayes' rule. So you could imagine looking at some other specification of belief updating, and that would not give you Burke-Nash equilibrium. That could give you Zhang Nash equilibrium if you come up with your right definition.
I see. Thank you very much. I guess maybe we'll have one last question from the audience. So Colin asked, how is Burke-Nash equilibrium different from Pareto optimality or even von Neumann's minimax condition? Or Colin, you want to unmute yourself? Ask.
Yeah, hello.
Okay.
Thank you for the opportunity. So my question is a very simple one, but maybe a fundamental one about the difference between this Burke-Nash equilibrium and Pareto optimality condition. And if you can also extend it to von Neumann's maximum and minimum, but that is also, that's for zero-sum games. But how is it, can this be extended?
Well, as we were just commenting, at least the version of Burke-Nash that we're using in this paper is for a decision problem. So in a decision problem, Pareto optimality is just optimality. And, you know, optimality given, Burke-Nash equilibria aren't optimal given the true distribution. People are optimizing given their beliefs, but it's not so, Yeah, so I just don't think there's anything really interesting to say about either Pareto optimality or zero-sum games here.
Yeah, I agree with this. A connection with games in terms of the definition of Burke-Nash equilibrium is that you can rephrase a Burke-Nash equilibrium in an individual decision problem as the outcome of a two-person game in which one of the players is the actual player that is selecting the strategy, and the other player is nature that is minimizing the Kuber-Leibler divergence given the strategy that is played by the player. So that's also the way in which you prove existence of Burke-Nash equilibrium. You rephrase it as but it's not a zero-sum game in general. So I don't think the von Neumann condition apply here. But it's a way to connect this Burke-Nash equilibrium in a single decision problem to a game.
That's fair.
Okay, so in the interest of time, maybe we could stop here. Let's thank Professor Fudenberg again for joining us today. Also thank Giacomo for joining us today. Thank you, everyone.
Thanks, everyone. Bye.
Bye.
Thanks.
Thank you.